assembly line, it's how the ordinary is actually extraordinary. Today on Some Assembly Required, knives, lawnmowers, and chocolate. The sushi knife. It's a knife unlike anything most people have in their kitchen. Super strong and razor sharp. And to make it, we need to work with the masters who have perfected the ancient art of metallurgy. Why do you need two different metals to make the perfect sushi knife? While Lou works at the forge in Virginia, I'm the lucky one who gets to travel all the way to here. We are in Sakai, Japan. And Sakai isn't just known for its knives. In fact, over 600 years ago, the first samurai swords were made right here in Sakai. And that DNA from that rich tradition of sword making can be found in every knife made in this city today. I'm on my way to one of the factories of the Korin Trading Company, one of the largest purveyors of the world's strongest knives. Though their factories are really a network of back alley shops. Well, there's an old joke in Japan, and it goes like this. A man walks into a knife-making workshop, and what happens, Paul?
You can't speak Japanese?
He can't speak Japanese. He can't understand anyone. That's why we have Paul Martin with us. Paul Martin is my trusty patient interpreter. He's going to help me cross the cultural divide as I learn to craft a sushi knife. I'm Brian. Making a razor-sharp knife that is both strong and flexible is a surprisingly difficult and complicated task. Kajira-san, a master knife maker, will instruct me on the methods essential to creating a strong, sharp knife. So tell me about the process. How does this begin?
First, he attaches a piece of hard steel, a bar of soft steel, and then he welds that together.
Kajira-san starts out with two different pieces of metal. One is soft iron, the other is high carbon steel. The secret to making a sturdy knife.
Hardened high carbon steel is so rigid and unyielding that it breaks rather than bending. Watch. If you try the same thing with low carbon steel, it bends rather than breaking. A composite steel needs to be created. The high and low carbon steels have to be welded together. High carbon for strength near the sharpened side, low carbon for flexibility along the spine. Making composite steel requires intense heat. When the metals begin to glow red hot, the structure of their iron crystals changes, allowing carbon atoms to dissolve in them, like salt in water. This softens the metal so that it can be pounded or forged well together. The crystals have to become completely entangled. You can only forge a perfect chef knife if the heat is perfectly regulated.
How hot is it inside the oven where the forge is next?
It's about 800 degrees.
800 degrees. On its way to more than 1200 degrees Celsius or 2200 Fahrenheit to weld these two pieces together. This is all done without any thermometer or anything to tell him what the temperature is. He's just doing it all from just sort of how he's feeling the heat and
the color of the steel.
And the color of the steel.
Yeah.
To say that these are handcrafted knives is almost an understatement. I mean, these are literally forged and shaped by hand from just crude steel.
Yes.
I mean, how many will he make in a day?
He usually makes 12 a day.
Just a dozen?
Yeah.
The belt hammer's pounding of the metal ensures flexibility. That's how the master does it. Now it's my turn.
You want to do that bit?
What?
Attaching the hard steel to the bar.
Do I want to attach the hard steel to the bar?
Mm-hmm.
Yeah, just have the ambulance pull up outside and just wait for me.
Is that a no?
See, Kajiro-san, thank you. Now, I'm looking basically down the throat of a breathing dragon. Sounds like bacon frying. Sounds like bacon frying. A lot hotter. Yeah. You don't have to tell him every stupid thing I say. This Japanese master is going to let me stamp out my own pieces of hard and soft metal.
Oh, he's going to leave you there on your own.
He's going to leave me here on my own.
Yeah.
You think Kajiro-san, is that a wise thing to do? So I'm just going to back off the heat with this lever here. Take this out. That's the hard part right there, is turning it. So I've got to turn the knife. It's getting a little crooked. Wait. I don't know if you can see this, but Kajiro-san is wearing flip-flops. Apparently these steel toe boots are really not a consideration. Oh, he wants me back here. So, like this? Kajiro-san, how am I doing?
Okay.
Okay? I think he's lying, but, you know,
You can have that as a present.
I can have this as a present?
Yeah, he's going to get it as a present.
Really? I can? Thank you very much. Thank you. No one will want to use that knife anyway since I made it. The knife has to be ground down to 1/4 inch thickness on its spine. This is the optimum width for a tool that needs to be strong, yet lightweight and flexible enough for the delicate work of slicing sushi. Then, it's stamped. This is really a very personal step where the maker actually begins to write his name in the blade that says where the knife has been made. You know, who would want to use a sushi knife anyway, made by someone from Dayton, Ohio? Well, the metal has its signature stamped in, but it's still a long, long way from being a real knife. Next, we have to prepare the steel to hold an edge. So this clay soup here, the quenching process means it will have lasting strength and sharpness. Kitsuo-san will actually apply sort of a porridge of water and clay to the blade. Once the clay dries, it's back into the fire where the blade is heated until it glows bright red. So this is kind of a second stage of heating the knife. They're actually reheated after this clay has been rubbed on the knife, so it's hardened.
Yeah. See him taking it in and out. He's trying to get an even temperature all the way along the blade. And then when he gets to the right temperature, then he'll crunch it into all the water here.
In doing so, we are once again altering the molecular structure.
Before heating, the steel contains tiny crystals of nearly pure iron, and its carbon is located outside those crystals. But at red heat, the carbon dissolves into the iron, and the steel becomes homogeneous. When you then quench the steel, the dissolved carbon atoms scramble frantically to get back out of the iron crystals, but they don't have time to escape. They're trapped. The resulting carbon-stuffed iron crystals are incredibly hard and at the heart of a good cutting edge.
Here in Japan, we're learning from the masters how to make the strongest, sharpest sushi knife. Having created a strong blade, now it's time to get to the point of sharpening. We're going to give this knife its edge. At the moment, it's not quite a knife. So we find ourselves in this sort of quiet residential alleyway in Sakai, where finally this blade gets its character. This knife becomes a knife. Hi there, I'm here to sharpen my knife. I think I found the right place. Hi, my name is Brian. Nice to meet you.
Nice to meet you.
Shinpei Ino has been honing blades for more than 35 years.
Now, this needs to become a knife. Now, I have to ask you before we get started, why is the water that these blades are stored in so green? I mean, it looks like antifreeze.
Oh, hey, to stop it from rusting.
To stop it from rusting?
The knives are raw metal. If exposed to the air around us, they begin to rust almost immediately. So they soak in a solution that halts corrosion.
Sort of an Edward Scissorhands look going on over here.
Now it's time to give our knife some real edge.
For centuries, this has been the way these knives have been made, on a stone wheel. Okay. Was the first blade that we forged, and it has no edge on it, and this is just after just a few minutes on the wheel where you can see the first edge has been applied.
The qualities of this unique steel allow the sushi knife to be honed to a severe angle, but unlike Western style knives, these are grinded by Japanese masters on just one side, allowing for unmatched sharpness and precision. A dull knife actually damages the cells in the fish, thereby altering the taste of the sushi.
Whatever you do, don't let go of that.
Don't let go of that no matter what happens. Okay.
This is extremely dangerous, and the trick here is to apply just the right amount of pressure at just the right angle, a skill gained after years of practice.
I'm doing a terrible job on that.
So you're moving it, you're not keeping it.
Keeping the angle. So the important part is to keep the same angle as I push it down. And I didn't ruin that knife, did I? Did I ruin that knife?
Oh, that damn it. If you kept going, you would.
If I kept going, I would have ruined it.
Obviously, the edge isn't finished yet. Using a smaller wheel than a whetstone, the blade is honed to razor quality sharpness.
Oh, you can cut your hair too.
Yeah. So
but I wear a toupee, so this is not necessary for me.
So,
oh shoot!
Everyone,
I felt that on my hair. I think this knife is done. Actually, it's not. It needs a handle. What we have here is a finished traditional Japanese carving knife, complete with its wooden handle. This is forged from carbon steel, handcrafted, and with the signatures carved into the blade. The only thing left is to actually use this bad boy. So we're at Uedea, and we brought our knife, the one we've been forging over the past couple of days. Paul, our trusty interpreter, you will take your seat at the bar. I'm going to go back into the kitchen. Oh, wait, I present to you the knife. Should I come across on this side and watch? Okay. Give it. Okay, I'm going to actually try now to, using our knife that we forged and made. This is the first time I've cut sashimi, so like this. Okay, and then he said to use the whole blade. Oh, wow. I'm making, You know what? Is it moving?
Yes, it is. He said it's still alive. It
is still alive.
Yeah.
That was good. I just got the worst heebie-jeebies. Oh, wait, that's not. This one's dead, right? Okay. Okay, so I have now completed this with the application of the lime. And behold, this lovely plate of sashimi.
These knives may be strong, but they're also amazingly delicate.
To give you an idea of how delicate these knives are, if you don't wipe them after every use, after one slice of the fish, it begins to rust. This is the knife we just made. And after I used it once, I've already kind of botched this knife and it needs repolishing.
Paul, next try.
No, I'm good, thanks. I don't eat fish.
Right. Can I get you a pint instead?
Yes, please.
You'll have a pint, no sashimi. Is that how it goes? Well, it is one of the great summertime rituals, mowing the grass. Some like to do figure eights, some like diagonals, some like straight up and down. But whatever your poison was, you had to admit, sure felt good leaving a nice, clean, mowed trail of yard behind you. How does a mower blade give your grass a perfectly even trim? Well, John Deere figured this out a long time ago. Their mowers are made of hundreds of parts working together to handle one simple job: cutting grass. And those machines are made here in Horicon, Wisconsin. Well, the assembly here at John Deere begins with this 30,000 pounds of steel. It's morning time here, and we're just using a 25-ton hoist to lift it. Excuse me, I have to press some steel. Now, they will go through about 2 of these giant coils of steel in about 4 to 6 hours. I gotta get one of these to move some stuff in my backyard. In less than 2 hours, that 26,000 pounds of shapeless steel will be pressed, cut, and molded into 1,500 smaller pieces, parts we're gonna need to build our tractor. Today, we're making the Select Series 300. Pretty amazing what a 1,000-ton press will do. Now, what's the gauge of this steel? It's a 3-millimeter stick. 3-millimeter stick. That's pretty big. That's why it takes 1,000 tons to stamp this. That pressure alone forces the steel into shape, changing its molecular structure without requiring any additional heat. Once we join together these metal parts, we'll have our frame. It'll hold the guts of this machine, the engine. Eventually, the frame will join with the fender deck, the part that the rider sits on. And I've got to stack 160 of these in an hour. It's all about strength right here, core strength. And I need about 20 more pounds on me to effectively use this for 8 hours in a day. Because this stuff is heavy. Once the heavy lifting's over, the fender decks will be washed and then coated in a primer to prevent rusting. And then they'll get painted a color that's pretty recognizable. That John Deere green is not a liquid paint. It's a powder. These robot spray guns are charging the powder electrically with high voltage. It comes out with negative charge, and it's attracted the positive charge on the metal part. The two stick together like socks coming out of a hot dryer.
There are some real advantages to electropainting. For one, this baked-on paint is less likely to run, and if anything is painted accidentally, it can be vacuumed away. That makes the process as green as the color. 99.9% of the excess paint is recovered and reused. The fender deck is done, so we're ready to start putting the rest of the lawn tractor together. And this baby is where you load all of these pieces into a frame. Now there are 15 of these. It'll be welded in 37 spots automatically, but Arnie and I here have to load this thing correctly. And at this point, I'm just getting in its way. Assembling a frame is a bit like putting together a puzzle, but Arnie Gorder could do it blindfolded. He's been working here for 29 years. This is the side of the frame, and I think it goes in... yeah. There is nothing intuitive about this. Oh yeah, it's a good thing he's here. Bye-bye.
Now it's the robot's turn to weld all the seams.
And voila! From behind the magic curtain, a finished welded frame. I've distracted Arnie. That completely screwed up the production here at John Deere. I broke the welder. Arnie, I was just bang on it. Well, we got all our parts. I'm gonna go build me a John Deere tractor.
Here in the assembly area of the factory, tractors are outfitted with all the parts that make them go, from the engine to the axles. Each piece is added separately as these machines go from bare frame to finished tractor.
Over here are fenders. In another area over here are some fuel tanks. The engines were added right over there. And over here, a dashboard assembly. All these things are just kind of swirling around each other in synchronous orbit to maximize the efficiency.
Adding all these parts is incredibly complicated, yet a brand new lawn tractor rolls off the assembly line every 56 seconds.
Everywhere. You gotta watch where you're going. They have these smart carts taking garden tractors from one part of the factory assembly to some other part of the assembly. It's a way of maximizing the efficiency of every worker here so that the part comes to them. It's pretty ingenious. This is how they do it. These carts, these smart carts, follow magnetic strips in the floor, and they're talking to each other by Ethernet, and off they go, nobody guiding them.
More than 20 different models of tractors are produced here. Smart carts tell workers what model they're assembling and which part it needs. And if a particular model doesn't require a certain part, the frame will just zip right on by. The smart system also tells workers at each individual substation what to make, how to build it, and when to attach it.
Even this little marker has a sensor right here that makes sure that when I do this and mark that these washers are facing the right direction, that I put it back. It senses it. Then there are cameras below here that make sure the dimples are facing upward on these washers. Even the torque wrench has a light that turns green, telling the main computer that the right amount of torque has been put on the blade.
That combination of human skill and automated assistance is critical considering how precisely constructed a lawnmower has to be.
So we have our freshly painted frames here for our lawn tractors. This is just one of the many sub-assemblies here at John Deere. And in this area, this is where the lawn tractor really starts to take shape. On these frames, the engine will be dropped in, the pedestal, which contains the steering column and some of the controls, and our mower deck. What are we doing exactly, Tanya?
Put on the hitch plate.
Hitch plate. Put it in the hitch plate.
And the axle.
It's the foundation for what we're making.
Correct.
Which is a four-wheel steering tractor.
This riding mower has a distinctive steering design. If you turn the steering wheel to the left, the front wheels go left. But unlike, say, a car, the rear wheels will actually go right. That kind of mechanism allows riders to make very tight turns, and it helps make sure that no patch of lawn goes unmowed. The experts at John Deere here in Horicon, Wisconsin are showing us how to make a lawn tractor.
This is where the rubber meets the road here at John Deere. Now, this has a pretty unique quality, this tractor. Four-wheel steering. I don't have that on my little hybrid car, but let me ask you something. It's like a fire engine with that long trailer in the back, right? Now, what kind of challenges does that present here to the folks at John Deere? It's very hard to supply both torque from the engine and steering to the same wheel. So they've attached the wheel not directly to the axle, but through a knuckle joint. This thing right here allows the engine to turn and therefore twist the wheel. At the same time, the wheel is steering.
Now it's time to attach the most crucial element of all, the almighty blade.
Dimple is up, dimple is up, dimple is up. Time to put some torque on. Torque. Oh yeah, that little green mark means I'm good. Torque.
The challenge is making sure that a single blade can produce an even cut of your lawn. One key is getting the grass to stand at attention. The mower does that with a curved portion on the end of the blade known as the sail.
It's cut like a wing as it rushes through the air like this. It kicks the air up and creates an updraft that basically carries the grass upward with it. Suction, airflow, suction, yeah.
All this precision comes down to physics.
The grass is inertial. It has inertia. An object at rest tends to stay at rest. What do you mean? This is the way the world works. Things that aren't moving, it's hard to get it moving. And that blade of grass is hard to get moving. If you come at it fast enough, you can slice right through it.
But you still have to have a sharp blade. A dull blade will tear grass instead of cutting it. This leads to water loss and brown grass. After the blade is set in place, it gets attached to the frame and mower deck. But we're not through yet, because without a system to run all of this, the blade would be useless.
Gene, I want to ask you a question. Gene Hayes is a design engineer here at John Deere. You can bring that in. We got a couple of things going on here. Now, when you're powering the mower, it's moving at one speed, fairly slow usually, but the blade's moving so fast underneath, and they're going at like, what, 200 RPM or something like that. How do you get two speeds out of one engine?
We've got two pulleys on here. The top pulley drives the transmission. The bottom pulley drives the mower deck.
So you got two belts going to two different places on two pulleys, basically. So without a pulley system like this, engineered to this degree, you couldn't do two things at once.
Correct.
You just drive over and then have someone cut it with scissors behind you? Yeah.
All that's left are the final touches.
Give it some force. Put some muscle into it.
This is where all the big pieces finally come together.
Up we go. Pull this baby out. Rotate her over. And under we go. Look at that. It's a marriage of two things. It's how they cut grass. Well, we are at the end of the line here at John Deere. This lawn tractor almost done, and these are the run-in men. This is Stan, that's John, and they're the run-in men because this is where we get to see if this deer can run. I'm ready. Go ahead and start. Oh yeah, it runs like a deer.
We are in San Francisco at the oldest family-owned and operated chocolate factory in the country. And the moment you walk into their lobby, you see the star of our piece, the cacao tree. Now, these grow 20 degrees above and below the equator, usually in a rainforest. This is a cacao pod, and in there are the cacao seeds from which we get the food of the gods, the chocolate. Whatever shape or size it comes in, chocolate satisfies our most intense sugar cravings. But ironically, the seed that makes chocolate isn't sweet at all. How do you go from bitter bean to butterfly? We are in the laboratory at Qatar Chocolates, and this is what? Flavor Central, right, Ed?
That's it.
This is where
it happens.
This is where it all happens. Ed Savine is the Vice President of Research and Development at Qatar Chocolates, and right before us, we see the bean.
These are the raw cocoa beans. This is what the farmers provide to us.
Before they get to Ed, the cocoa beans and their pulp must spend days fermenting and drying out. From their initial flavor, you'd never guess what's going to come out of them. What would this taste like if we were just to bite into this now? Would I get a chocolatey sensation?
Absolutely not. It would be the last thing you'd taste.
What would I taste?
It's going to be bitter.
It's going to be astringent. There will be some interesting floral aromatics in there, but it will be totally lacking of chocolate.
Here's a total disappointment. To inspect the beans, a sampling of them makes its way into the lab and into this contraption known as the bean guillotine.
Nice. Pretty efficient. And probably sharp.
Unfortunately, yes.
You speak from experience?
No, because I have all
you guys to say all the tips of your fingers are there and everything else. All right.
From the looks of them, the fermentation has been done really nicely on this particular lot of beans.
Mm-hmm.
You see the nice fissuring in these beans over here?
Yeah, like little splintered.
That's
sort
right.
of inside.
They're separating inside.
Fermentation has literally killed the beans and in the process started to change their flavor by destroying some of the bitter tasting molecules.
Notice the smell. You can smell. There's an interesting fragrance that comes off of that.
They actually smell vinegary.
Yeah, they do.
They don't smell pleasant. I mean, it's not like you're getting this big chocolate wafting deliciousness coming out of there.
No chocolate whatsoever.
Yeah, not
at this point.
Okay.
From rainforests around the world,
Ghana, Ecuador, Ivory Coast,
sackfuls of beans sit here in the warehouse till Ed gives the nod.
I suppose you'll go through what? All of these in a day?
These beans are the product of the cacao tree's survival method. It's evolved so that when birds eat the sweet pulp of the pods, they spit out the bitter beans onto the ground, which brings us to step one, washing the beans.
You gotta clean the beans.
Hey, anything that's been laid out in the sun for a week or two in the jungle, every high-stepping critter, low-flying varmint spin across it. I want to clean them.
Gotta watch out for them varmints.
Her love has to go through 5,000 pounds of beans in one day. It makes it look so fun, I want in.
Well, can I do one? What do you do? Just right here? Just rip it open?
The beans pour down this grate to get clean. Then they ride up an elevator to get roasted.
This is a very, very noisy area. This is where they roast the beans. Now, Ed, how hot are you making these beans here?
Hot enough to bring out all the flavor, and beyond that, I'd have to kill you if I told you.
Okay.
Roasting the cocoa beans is one of the most critical steps in creating the chocolate flavor.
Roasting transforms all the flavor precursor molecules into the scents that we identify as chocolate. Among those precursors are amino acids, the building blocks of proteins. And when you heat those in the presence of natural sugars already in the beans, they develop into these wonderful aromatic flavors.
The roasted bean is shelled, and what's left is the center.
This right here, that's the good part. That's what you want.
It's the nib.
The nib.
The nibs have to be cooked just right. Over-roasting or under-roasting can lead to bad-tasting chocolate. So Ed and I do a flavor check.
Now, what will this taste like?
This will begin to taste like chocolate. It's got a little bit more of a brown egg note right now.
Yeah.
But if you continue to chew it, you'll get more chocolate flavor out.
Like a nut. Like a chocolate nut, you know? Good.
The nibs pass Ed's approval and become the foundation of the chocolate butterflies we'll be making later, but we can't use them like this. To turn this nib into edible treats, we have to go from solid to liquid, to solid to liquid, to solid to liquid, back to solid. Stick with me, folks. It's gonna be a wild ride. Okay, the first thing we do is grind up the solid nib.
Basically, we're just reducing that chocolate seed, these nibs, to its liquid form. This is called chocolate liquor. Now, there's no booze in it. It contains cocoa and cocoa butter.
Because cocoa butter's melting point is just below body temperature, it gives chocolate that melt in your mouth quality.
To get the smoothest, silkiest chocolate, Guittard has to add extra cocoa butter to its cocoa liquor. It gets that cocoa butter by extracting it from a portion of cocoa liquor in this press, which exerts 2 million pounds of force on a cylinder full of cocoa liquor and squeezes out the cocoa butter.
But combining extra cocoa butter with cocoa liquor doesn't make chocolate. We need a few more ingredients. We have made all of our ingredients, right?
That's correct.
And now we need to mix them to actually start making chocolate.
He's mixing some basic ingredients together.
But on an enormous scale, you do this.
Our mixing bowl is 5,000 pounds.
A lot of buttons, a lot of lights. Looks confusing. This is a machine straight out of Willy Wonka. The cocoa butter, the liquor surge tank. Now you're going to put those into this little line. This little line is going to feed into these two digital readouts.
Correct.
Sugar. No. If I follow this line upward, it's going to take me back over.
No, you missed.
I missed right here. This vertical
It's over there.
right here. This isn't complicated at all, Ed.
No, it's just a transfer.
Ed here has a PhD in flavor science, but even he's having some trouble figuring out this machine.
Start, pull
Pull
the
on
mixer
this
in
one?
motor. Yep. That's good. Let it go. We have to do it again.
Okay.
I didn't have that pulled out. Go ahead and pull it out again.
Ed, you work here?
Yeah.
Oh, I heard something.
No, you heard a door shut on the other side of the wall.
Finally, we get things going. Let's give it another drop, and then I'll switch it back.
Right about where we ought to be.
And now we head back down to the floor for another flavor check. We could walk out of the room, but the whole crew is
in the way.
All of our ingredients are in. And like a vintner checking his grapes at each winemaking step, Ed constantly monitors the development of his chocolate. At this point, the texture is nowhere near what he wants.
This is kind of gritty. It feels a little gritty. Yep.
But the flavor is getting much closer.
Tastes just like chocolate. Pretty good. You'll taste the milk in it? Yeah.
A quick pass through 5 massive rolling pins pulverizes the gritty paste.
These refiners turn this pasty stuff into a dry powder by exposing a whole lot of new surface area. The particles, as they go through the refiner, are ground down to less than a 2,000 inch diameter. The fat just can't cover those surfaces well, and it's left as a powder.
How do you get it to become a flake? We're not taking anything away. We're not adding it. Just making it fine. Turns it into a powdery flake until it's mixed again. Now, is that smooth? That is delicious.
At this point in the process, our chocolate is packed with flavor, but there are still some unsavory molecules. Plus, we have to turn this powder into an easy-flowing liquid. A tall order involving heat and a monstrous mixer.
This part of our chocolate assembly is called conching, named after this scary machine, a big giant blender you'd find in a horror movie. It's where our finely ground milk chocolate powder is dumped, and it's blended and mixed together for hours and hours and hours, sometimes days, depending on how expensive the chocolate is. It kind of stews in the heat and its own juices, and that enhances flavor. The acidity in all that chocolate liquor is released, and eventually this turns into a thick chocolate syrup.
Liquid chocolate is great if you want to drink your candy bar. Guittard ships out their confection-making chocolate in solid hunks, so we'll have to harden our syrup. But we don't just cool it down. Oh no, that would be way too easy.
Now, in order for Guittard to make a chocolate bar that holds together as a solid at room temperature, they have to put it through a process called tempering. That's kind of a fancy way of saying they heat the chocolate up, cool it down, and then bring the temperature back up. From there, they feed that heated chocolate through a system of pipes and then fill these trays with what is finished guitar chocolate bars.
The multiple changes in temperature lets the fats crystallize properly, giving our chocolate its characteristic gloss and snap.
Delicious.
These 10-pounders are getting packed and shipped to confectioners around the world.
Guitar. Check out that big honka slab of chocolate deliciousness right there. Here they come. But most of this is going to confectioners who will turn it into other candies. This happens to be a mild dark chocolate. I gotta tell you, this kind. Did you know that we consume 3.5 billion pounds of chocolate every year in this country? What is wrong with us? Nothing is good for you.
One of these 1,500-pound boxes is delivered locally to Charles Chocolates, where those big bars become perfectly little bites of candy.
I'll tell you what, I never miss an opportunity to wear a good hairnet.
You know, I'm the same way.
Chocolate artisans make up a tiny portion of a $13 billion a year industry.
All right, Charles. This is our guitar chocolate that Lou and I made.
Absolutely.
We're going to turn it into something so beautiful like that.
Exactly.
Which is really the fanciest peanut butter cup I've ever seen, I got to tell you.
Well, it's probably the best one you'll ever taste.
Yeah, I'm looking forward to it.
To make these delicious peanut butterflies, we first melt our 10-pound bars, but melting destroys the crystals formed when we temper the chocolate back at Guittard. So, before we use it here, we temper it. Again,
You temper the crap out of chocolate, it seems.
One of the nice things about chocolate is, at the end of the day, whatever chocolate we haven't used, we can reheat it. And then come back tomorrow morning and temper it again. And there's no ill effect.
You have to keep retempering because it'll over-temper after a while, right? The secrets
Exactly.
got too big and too many.
It's easy to identify. The chocolate gets thick, it gets gloppy, and we know at a glance that we've gone too far and we need to start over again.
You just got to put it right under there.
Just put it
You
right
just
under.
got to do the thing.
Exactly.
if we've over-tempered our chocolate, we have an even bigger problem. Our butterflies will stick to the mold. Luckily, we've done everything right, and they pop out easily, so we just keep going.
Inside this plastic bag is the peanut pralinette,
Correct.
or as I call it, liquid peanut butter.
Or you can call it liquid peanut butter.
And
I'll only take a little offense.
you feel this in your back.
Not when you're my size. One of the advantages of being short.
Being a little shorter.
The last step is sealing up our candies with a final layer.
This is probably the easiest part of the whole process.
Okay. You kind of missed this part, right?
Yeah, I noticed that. I'm going to fix that.
A few hours with Charles, and I've yet to make a Charlie in the Chocolate Factory reference. Oh, wait, I just did.
We just tap it a little bit.
There it is. From bean to butterfly. Oh, no.
Hard to believe this sweet little thing had such a bitter beginning.
Yeah. Hey, what is that over there?